Okay, so we now move into Chapter 5, and how far we get in Chapter 5 is yet to be seen with all of the interruptions we've had this semester. But what we want to do is we want to study the logarithmic functions, exponential functions. In other words, we're no longer studying algebraic or trigonometric functions. This is a new type of function that you would have been introduced to in your pre-calculus classes. Hopefully well. Hopefully it was taught well to you, because they are incredibly interesting functions. And let me start by asking a simple question. What if you wanted to integrate 1 over x with respect to x? Well, you may begin by noticing, well, I can rewrite 1 over x as x to the power of -1, and then proceed to my integration. But if you recall, there was a caveat in the general power rule for integration that said that you could use this rule where you add 1 to the exponent, x to the n plus 1 over n plus 1, except under the situation where your exponent itself is -1, right? I mean, you can see that if you place a -1 here, you would have -1 plus 1, you would be dividing by 0. So you can see why the caveat has made it into the definition. But because of that, we have not yet been able to integrate a function that looks like this, x to the -1. And now we're going to turn our focus to that caveat. And we're going to do so, but let's start with the definition of the natural logarithmic function. And before we do that, maybe it's worth understanding that if you begin with an exponential function, ready? So if you don't mind, I'm going to erase everything I'm about to write. And in fact, I'll change the colors just so you don't have to take any notes right now. If you start with an exponential function, right? So let's say 2 to the power of x. Now, exponential functions look innocent, right? If you were to start to play this game where you would choose an x and then plug it in. Well, in the beginning, if x is 1, 2 to the power of 1 is 2. If x is 2, 2 to the power of 2 is 4. If x is 3, 2 to the power of 3 is 8. Again, it looks quite innocent in the beginning. And now let me go ahead and make a statement that if you're like me, if you enjoy let's say zombie movies, then let me tell you that the reason why everyone is running in your zombie movies is because of this exponential growth, right? I could make the statement that it's really a logarithmic growth, because eventually, if everyone becomes zombies, the growth rates start to decline. But in the beginning, it's going to look exponential. So let me not go into that part. But ready? Let's just say that this x represents hours, and 2 to the x represents how many zombies there are. Ready? So the first hour, there are 2 zombies. Second hour, there are 4 zombies. The third hour, there are 8 zombies. Again, everything looks innocent. Now, I'm going to ask you a question. Of course, I can't call on you to answer it, but I want you, if you don't mind, to take a guess in your head of how many zombies you think will be around after 24 hours. And before you grab your calculator, what I'm trying to demonstrate is how unbelievably unintuitive exponential growth is. So you should take a guess before you plug this into your calculator, because I want to show you why you're probably pretty bad at this, as am I. So 2 to the power of 24, I'm going to write the number and then I'll put the commas where they need to be. Would look like this. Now, if you were thinking over 16 million zombies after 24 hours, then that's fairly good. And the majority of us, if I said after 1 hour there's 2, after 2 hours there's 4, after 3 hours there's 8, if I asked most individuals in 24 hours how many zombies are there, some might say, in the thousands, some might say maybe in the hundreds, some might even say 1 million, but the fact that you can see how this can get out of control really, really quickly. Exponential growth is quite beautiful and quite scary, and depending on your application. Now, what I want you to understand is, because now what I want to do is talk about what a logarithmic function is. And I will tie this back to the natural logarithmic function, which is ln. But what I want you to understand right now is this is not an algebraic function. You can't solve for x the way you would solve for x normally, right? If I say y is equal to 2x and I ask you to solve that for x, that's very easy. You just divide both sides by 2. If I tell you that y is equal to 2 to the power of x, this is different. This is a different type of function. And we can't use algebraic techniques for these types of functions. So how do we solve? Well, let me make this very brief. A log, if you had one word, if somebody said, in one word, can you tell me what a logarithm is? Here's what you would tell that individual in one word. A logarithm is an exponent. I'll say that again. What is a logarithm in one word? What is a log? It is an exponent. In other words, logarithms are how you solve for that x. Okay. Now, what I want to do is I want to talk about ln. So, in this particular case, let's look at that f of x is equal to 2 to the power of x. Let's you and I agree that the base of that is 2. The x is your exponent. Now, if you were going to introduce a log, you would have to have a log of base 2. You don't have to, there's ways to change base, but the idea is the log base 2 would equal that exponent. Okay? Now, all I want to do is I want to talk to you about what are some types of bases. So there's some limitations, but there's all types of bases that you can use. Base 2, base 10. But there's two bases that have or tend to show up more often. So for example, base 10, and the next one is base E. I'll talk to you about E in a little bit. So all I need you to understand now is when you have a base of E, you can think about the log of base E. Because ln, this ln of x, is just a log. It's a logarithm. Now, they call it the natural logarithm, but it's a logarithm with a base of E. So it's so unbelievably useful for reasons not yet given is that it actually has its own button, right? So you have a log button on your calculator, and you can use that for all bases that you would like, but you also have this ln button on your calculator, and that's just this one particular log that has a base of e, okay? So what is an ln? An ln is a logarithm, but it is a logarithm with a special base, a base that is we call e. All right, now that's a little bit of preliminaries out of the way. Let's actually get into the crux of this presentation here. Now, the definition of a natural logarithm, right? What is an ln of x? We can go back to that notation that we were using in the previous chapter, where notice how we have that integral of 1 to x, and then there's this t inside here. Well, now look, that t is just a dummy variable. It's a placeholder variable for right now. And the idea is if you were to integrate this with respect to t, when all is said and done, what you will get is ln of x. And let's actually do it. Ready? So I'm going to integrate 1 over t with respect to t, and let's go ahead and do that. So that would be the integral of 1 over t is ln of t, to which we want to back substitute 1 to x. Ready? So we have to do f of x minus f of 1. Now, plugging in x for t, that's ln of t minus ln of 1. Now, what is ln of 1? Well, you can try it on your calculator. Ln of 1 is just equal to 0. And if we just think about that for a second, if we think about the fact that ln of 1 being equal to 0, well, let's think about that as an exponential function. So that would be a base of e, Now, since I said a logarithm is always an exponent, that 0 would go right here. And what's inside the logarithm would go right here. Now, does that make sense that anything to the power of 0 is going to be equal to 1? I shouldn't speak in absolutes, right? Aside from talking about 0 to the power of 0 or infinity or something else like that, but anything to the power of 0 is 1. So if e to the power of 0 is 1, then that would mean what? That would mean that that your ln of 1 is going to be equal to 0, right? I could rewrite this. Well, I won't go any farther than that. It's just going to be equal to 0. All right, now, so we're left with just, my sincere apologies. I put a t here. Did you notice that as well? You probably did. But how dare you not tell me over the internet? So that zeroes out, and you're left with just ln of x. Okay, now, so what you're noticing here is the graph of 1 over t. Right, so you can see the graph. Now, when you're choosing x values, right, so remember the integral, we get this ln of x. So what they're really pointing out is that when you choose x values between 0 and 1, or when you choose x values greater than 1. Now you can't. So we can't choose negative x values. You can, you could look at the graph if you wanted to. You could, more importantly, you could look at the graph of your logs or ln. You can see how you won't have negative x values anywhere in the graph. But what's important to notice is that if you choose x values between 0 and 1 or x values greater than 1, then what you're going to end up with is an ln value that's greater than 0 or an ln value that is less than 0. Now, I'm going to explain that a little bit more. So if you feel like that didn't quite take, then just hold off for just a second, and it'll become more apparent when we look at the graph of ln. So let me pose a question to you. What is if you were to integrate, let's say 1 over t with respect to t, but what if your upper bound is equal to your lower bound? How would you think about the area of that? Now, this is true for any function. I'm just speaking of ln, but when the upper bound is equal to the lower bound. Now, of course, we have definite integration, right? I mean, we're not going to have plus c's when we have these upper and lower bounds. We're going to get a single answer, and that single answer is an area. But my question still stands. How would you think about the area under a curve from 1 to 1? Well, let's think about if you start at 1, right? So here's where x is equal to 1. But you stop at 1. Do you have any area at all? No. I mean, you have to have at least a height and a width, a length and a width to start talking about area. You just have a line. You have a one-dimensional line. You don't have an area in one dimension. An area is, by definition, two-dimensional. So hopefully that also will help you understand why the ln of 1 is equal to 0. Now, a couple properties to take note of, right? So some properties of you, and you shouldn't gloss over this, because we're going to be talking about ln and e a lot, and you really should have a pretty good feel for the domain and the range and so forth with just some basic properties of your graph of your natural log. So what you're looking at here is the graph of ln of x, and some things to kind of take note of is let's start with the domain. Do you see how your graph never crosses that y-axis, right? In other words, it's never on this side of the x-axis. So it will continue in this fashion, but you will both never reach 0, nor will you reach the negative x values. So the domain, you can try this. You can try ln of 0 on your calculator. You can try ln of -2 on your calculator. It will give you an error. So the domain is from 0 to infinity. The range, meaning looking at the y values, well, the range is going to go from -infinity, and this is going to continue to climb into -infinity to +infinity. And now that makes sense if you were to compare it to the exponential function, which, if you recall, these would swap. The domain and the range would swap. Now, another thing to take note of is the ln function is always continuous, right? So there's no breaks. You don't have to lift your marker when drawing it. It is always increasing, and it is 1-to-1, meaning you can find the inverse of it. Now, you could show that it's always increasing. Well, you could look at the graph, but you could also just look at the derivative, right? The derivative, if the integral of 1 over x is ln of x, then the derivative of ln of x is going to be what? Well, it's just going to be 1 over x. Now, 1 over x is always positive if you're going to choose x values greater than 0, right? This will, so if for x values greater than 0, this will always be positive. And what do you know about derivatives? Derivatives tell you if you have a positive derivative, you have your graph is increasing, right? If you have negative derivatives, your graph is decreasing. So this is a strictly monotonic function. It's always increasing throughout its entire domain. Now, it's also always concave down. And right, you can see the concavity throughout the entirety of the graph. And again, you could just look at the second derivative. Now, in that case, you would have x to the negative 1, which would leave you with negative 1 over x squared. Now, in this particular case, for all x values greater than 0, your second derivative is always negative, right? If you plug in a 2, that would be negative 1 over 2 squared, or negative 1/4. So if your second derivative is always negative, then you can see why it would always be concave down. Now, if you're noticing these, and this is somewhat hard to show on this tablet, but if you notice these little lines, right? These are actually little slopes. If you depending on how far you have to go in mathematics, in say probably differential equations, maybe even in your calculus classes, depending on your professor, at some point in time you will be introduced to slope fields. And since ln of x, once you integrate, you're always going to have the plus c. You can just imagine that these are just all the different graphs of ln, right? Each graph, depending on the value of c, they're just vertical shifts. They're just vertical translations. Now, some of the basic log properties that you would have picked up on in your pre-calculus class are going to be important for where we're going to go, and I'm not going to take for granted that you either remember or even learn them the first time you were introduced. So I want to say them, and then I want to practice them very quickly, right? So I've already shown you that ln of 1 is 0. Ln of AB is just simply equal to ln of A plus ln of B. Again, don't gloss over these, because you're going to need the log properties to do the calculus of logs. So the product rule would say ln of A times B is equal to ln of A plus ln of B. You can go forward or backwards here. The quotient rule says ln of A over B is just simply equal to ln of A minus ln of B. And one of the most amazing and helpful properties of logs is this guy right here. And to make sure you can see it, the fact that ln of A to the power of n is equal to n ln of A is one of the most helpful facts of these log properties. So again, imagine you wanted to solve for n. Well, what would that even mean, to solve for n? If you know anything about earthquakes, there's various magnitudes, right, of different earthquakes. Now, a magnitude is the n. So when you start talking about a 6 on a Richter scale, or a 5 or something like that, you are discussing the magnitude. And notice how it's very nice that the n can be brought out front, like so that you basically can start to use some of your algebraic techniques So now you could just divide by ln a if you were trying to solve for n. Okay, now let's go ahead and practice a few of these really quickly. So this shouldn't take us long. So ln of 10/9, that's just a quotient rule, right? That would be ln of 10 minus ln of 9. Very simple. Let's actually do the third one before we do the second one. So you have multiple things going on here. You have ln of 6 multiplied by x. Now that's a product divided by 5. So first let's start with the quotient. So this would be ln of 6 times x minus ln of 5. Now that part most students would notice, except that you're not done if you're trying to fully expand. You would now take ln of, that's a product rule, right? So we would have to use our ln of a plus ln of b. So this would end up being ln of 6 plus ln of x minus ln of 5, right? So this ends up being a product rule here. Now this second one, the first thing we want to do is we want to rewrite ln's without the radicals. So we want to have 3x plus 2, and that's going to be to the power of 1/2. And now, since all we're trying to do is use our log properties, we're just going to take this 1/2 and bring it out front of the natural log, just like our property allows us to do. So that ends up being 1/2 ln of 3x plus 2. Okay. Now, so let's discuss e, base e, number e, for just a quick second here. Oh, I'll tell you what, let me do it this way. Okay, so if we stay in the real number system, right, no complex numbers, no imaginary units. If we stay in the real number system, then all the numbers that you could think of would lie somewhere on this number line, right? They're all equally important, I guess you could say, or I guess you could argue, but there are certain numbers that just lend itself to the types of to answer the types of questions we like to ask. And now, for example, the number pi would be on this number line. Right, let's just say it's here. That's it's an irrational number. You cannot express it as a fraction. And it would go on forever, non-terminating decimal without any predictable pattern. It is a irrational number. Now, another extremely important number is the number e. Now, just as an approximation, e is 2.71828 and so forth. Just like pi, you could say is 3.1415 and so forth. But it is also a number on this number line. It too is, oh, my apologies. It too is an irrational, non-terminating number that can't be expressed as a fraction. Now, when I say as a fraction, of course, you can write pi over 1, right? That's trivial. But it can't be expressed as a ratio of two other numbers. But e is again just a number that lies on your number line that just lends itself to to many applications. Now, one of the most intriguing, well, let me actually not get ahead of myself. Let's start with, if you wanted to take ln of e. Well, I mean, I could go through, how we define with our original definition of ln, but I think if you think about it this way, if ln, I'm going to go ahead and erase this number line. If ln, if your natural log is just a special logarithm, right? It's just a log with a base of e. So really, what we're saying, when we say ln of e is 1, well, let's think about, well, I don't know how long I want to stay here, but if we think about this in exponential form, right? This is, if we think about, since our natural log is just a special logarithm, we could think about e, base e, to the power of, remember, this is your base, so this is your exponent here, so e to the power of 1. Well, what is e to the power of 1? What must it equal? Well, it must equal e, right? So that's the way and why you can think about when you take log of base e of what? Of e, you get 1. Now, if that's a little bit too much, no worries. Here's all I need you to understand right now. The only where did I just go? Did I go to differential equations? I don't know where I went. So the only thing I need you to be able to take away right now is that e is a number on the number line, just like 3 is a number on the number line. And I need you to understand that ln of e is equal to 1. Okay. In fact, let's just stay here. E to the, well, I don't want to jump ahead, but e to the ln is also equal to 1. All right. Let me now go ahead and get to, I'm gonna take a break here in just a second. I want to go ahead, because this, for a section on calculus, there, I think you and I can agree there hasn't been a lot of calculus this video, and I want to go ahead and explain to you how do you take the derivatives of ln's. And it's they're very easy. They truly are. So all I'm going to do is rewrite what is in this theorem. So the derivative of ln of x with respect to x is just 1 over x. Now, the caveat is of course that x cannot be greater than 0, but that's just because that was, if you remember, the domain restrictions of ln. So that is the derivative of ln of x. Now, let's take a look at the second one, because sometimes that confuses students, because now they say the derivative with respect to x of ln of, and then they put a u, and a lot of students would think, well, wait a minute, u is a variable, just like x is a variable. So why isn't, my apologies, the derivative of ln of u just 1 over u? Okay, so now let me go ahead and discuss that. What they really don't explain well here is, if in this particular case, this is ln of just x, right? There's nothing else inside here, just x. But if you have anything else inside of your ln, right, let's say 2x or x squared or so forth, if you have more going on inside of your natural log than just x, then what you do is write that as u prime over u. Okay, this is going to be, listen, I'm telling you, this and this are so easy. You just need to see an example. Watch, let's just do these really quickly, very easy. So I'm going to write off to the side. The derivative of ln of u is just u prime over u. Okay, I'm just rewriting this guy here. All right, ready? Let's watch how easy this is. So let's start with part A. So in this case, let's let u equal 2x. Then what's u prime? 2. So the derivative of ln of 2x is going to be u prime over u. So what is that? Well, that's just 2 over 2x, right? Which is just simply equal to 1 over x. Now that I know that is super easy. In fact, you could have actually thought about it as bringing. Well, no, let me not go through. It's like when I ask my grandfather for directions, and he gives me 3 or 4 different ways to get there. It's nice, but most of the times we want one way, right? So never mind. So now let's do part B. So in this case, we're going to take the derivative of ln of x squared plus 1. All right, no problem. So we need u to define u, and we need to define u prime. So easy enough. U would be x squared plus 1. U prime would be 2x. So u prime over u, worst looking u in the history of the u. Well, that would just be 2x over x squared plus 1. Didn't I tell you that this is pretty darn easy? Right? That's not bad. Okay, well, let's do this here. Now, this is a product, so we got to be a little bit careful here. So just revisiting our product rule. So if we let f of x equal x, and we let g of x equal ln of x, well, then you would need f prime of x, and you would need g prime of x. But once you have all that information, it's just f prime of x times g of x. If you don't mind, since I am low on space, I'm just going to write it without the of x. So that's f prime multiplied by g plus f multiplied by g prime, okay, without the of x part. So, okay, well, let's go ahead and answer this. Well, f prime of x, well, if f of x is x, then the derivative of x is just 1. And g prime of x, well, the derivative of ln of x is just 1 over x. Easy, right? So let's just put everything in the right spot. So f prime, this would be 1 over x. 1 over x multiplied by ln of x plus 1 multiplied by, why did I do it that way? See when I moved that thing, I got ahead of myself. Let's try that again. F prime is just 1. G is ln of x plus f, regular f, is just x, and then g prime is 1 over x. Now, any more silly mistakes? I think we're good. Okay, so f prime times g, 1 times ln is just ln of x, plus, well, I'll write this, but I think you can see that that's really, well, I'll tell you what, I'll draw it up here. That's x times 1 over x is just x over x. right? So that's plus 1. All right, last one. Ready? So looks like we have ln of, I'm sorry, the derivative of ln x to the power of 3. Now, in this case, you would want to think about the chain rule. You would want to think about u, in this case, being ln of x, then f of u being a u to the power of 3. And then we would need f prime of u, and then you would need u prime. Well, f prime of u, well, the derivative of u cubed is 3u squared. And the derivative u prime is just 1 over, what? 1 over x. Okay, so the chain rule, if you recall, the chain rule would be the f prime of u multiplied by u prime. And now let's just put everything in the right place. Right? So f prime of u would go here, u prime would go here. Now, in the end, we have to plug back for u. You can do that right now if you wanted to. For this problem, I'm just going to go ahead and write f prime of u is 3u squared multiplied by u prime is 1 over x, and now I need to go back and put the ln back in for u. So this ends up being 3 ln of x squared times 1 over x. All right, now you can clean that up if you want, but you for the most part, you can now see how we can do some basic differentiation. So I can't, to be honest, I really can't complicate this in the sense of how to take multiple derivatives. So you will get more practice at this when you do your homework. When we come back for the second part of this video, I want to show you a technique that you can use that's very helpful, and we'll talk a little bit about the logs of trig functions. But again, do you agree with me? That's not bad, u prime over u. So come on back and we'll finish this section.